So good morning all and welcome once again in the fourth day of this service-sponsored AI and machine learning workshop on healthcare. So it's my immense pleasure to introduce our keynote speaker, Dr. Vikesh Kumar sir, who is currently working as an associate professor in the discipline of biomedical engineering at NIT Raipur, India. He received his Bachelor of Engineering degree with honors in Electronics and Communication Engineering from Pandit Ravi Shankar Shukla University, Raipur in 2004. The MTech degree with honors in Instrumentation and Control Engineering from CSBTU, India in 2006 and his PhD degree in the discipline of biomedical engineering at NIT Raipur in 2015. His research interest biomedical signal processing, EEG, PPG, lung sound, medical image processing and analysis, computational neuroscience, computer-aided diagnosis, deep learning, machine learning application in a healthcare. He has several awards and honors like IET Gauri Memorial Award, IEI Young Engineer Award, Chhattisgarh Young Scientist Award, Gold Medalist Award in BE for the first rank in the university, Best Paper Award in the International Conference of Nanotechnology and Biosensor at REC, Visakhapatnam, and many more awards in his credit. He has 125 publications, which includes the journal paper, conferences paper, books, and book chapter. He has guided the 8 PhD scholar, 6 MTech scholar. He has also worked on the 5 research projects funded by the DST, CSIR, CG Cost, SERB, ICMR. He has also delivered more than 16 expert talks and the lecture in the conferences, workshop, and the short-term courses organized by the various institutes. So this was just a brief bio about the sir for his tremendous work experience. Now I would request to invite Dr. Vikesh Singh sir to please start the lecture, sir, please.
Thank you very much for the nice introduction.
Thank you, sir. Forward, backward. This is for forward. This is for backward. This is for the long press. Forward press. Forward. Okay.
I think. So I'll be discussing not on much hi-fi thing. I'll try to discuss some fundamentals. I'll discuss some of the studies which are at the end of the lecture. But before that, I have divided this whole lecture into 3 parts. First, I'll be discussing something about machine learning and the journey from machine learning to deep learning. And then I'll be discussing in the second part, I'll be discussing something about EEG because in our lab we are doing some work on EEG. So I'll discuss some fundamentals of EEG, not much detail, and some fundamental signal processing techniques. And after that, at the end, I'll be discussing some of our works on respiratory sounds, which we have done in, we are still doing, but I'll be discussing some preliminary results, what we have obtained on our respiratory sounds. The works which we are doing in our lab is based on EEG, but we have done some respiratory sounds based study also. So that is still continued, but I'll be discussing whatever preliminary paper and results we have obtained that I'll be discussing. And after that, we'll also see, I'll just in the last slide, I've put what are the different works we are doing in my lab. So I'll also discuss very brief about the different studies that we are doing in our laboratory. So in the first part of my, as you can see in the title, machine learning pipeline for biomedical signal analysis. biomedical signal analysis is a very broad term. There are a lot of biomedical signals which originate from our body, like EEG, PPG, PCG, and many other like respiratory sounds. So many biomedical signals are there, and I have focused in this particular presentation. I will be focusing on respiratory sounds and EEG. So I want to put a disclaimer here that most of the contents of this presentation are taken from different internet sources and books and some of my published research articles. And I sincerely acknowledge and I've also used some of the contents from my published research articles. I sincerely acknowledge all these sources and there are no conflicts of interest. So I'll start with this traditional programming versus machine learning. I'll give a brief introduction of the pipeline of machine learning, which is to be followed in any medical research, and then we'll move to the signal processing part. Okay. So the traditional programming and machine learning, the basic difference is that in traditional programming, as you can see, that we give a data and a program. Program is pre-available. We design a program, we give data, and we get the output. There is no learning in traditional programming. Okay, we give data, we have a program, that data is input to the given program and we get the output. That is the traditional programming. But in machine learning, as you can see, that data and output are given to the computer and the program is available to us. So program is made here also, but the program is not made from the given input only. And that's why we say that there are two parts in machine learning. One is called training and other is called testing. So training here basically means that whatever data is available with us, that data helps us to write the program. We write a generic program first, but during the training, that program becomes more accurate. That program becomes more accurate. Okay, so that training itself means that we are making the program more accurate so that it can be later used for some real-time application. Okay. So in case of machine learning, we have this data with us. This data and the desirable output, they help us to make a program with the help of process which is called training in machine learning. In machine learning, we have training and testing. So this training is actually what? We have data, we have some desired output. These two help us to make a program, and then this program is used for. So we have a program. We have a machine learning model which is trained with many existing problems. So this problem means we have both data and output. So these data and output helps us to make a program, and this program is such that whenever you present a new problem to the program, it is able to give the output. This is the basic difference between traditional programming and machine learning. In machine learning, the machine learns. Why it learns? Because you give two types of data. One is the input data. That is, it can be any type of data. It can be signal or it can be image, and you also give the corresponding output. So because you give both data and output, because of this data and output, the model learns that okay, if this is the data, this should be output. If this is the data, this should be output. So in this way, the model learns, and this process is called training. And then once we have a trained model available with us, we can give new problem to the model and we can check whether the model is working properly or not. So why this machine learning, deep learning, these things are required? Earlier, when we had this when the main problem in these type of studies, that is the medical studies, the availability of data. Okay, if I say 10 years ago when we were doing PhD, the main problem was getting the data. It was very difficult to store large amount of data in hospitals because that time there was not so much computing and facility, and information technology was not so advanced that time, around 20 years back, if I say. So the biggest problem was the availability of data. And since data was not available in huge amount, machine learning was suitable that time, because machine learning is not data hungry. Though we say that still, if you give more data, your model will be better trained and you will get high accuracy. But in case of But that problem does not exist today. Today, availability of data is not a problem. We have so many open repositories where you can find so much of data, either image data or signal data, and many other types of data. And nowadays, even hospitals data with themselves because of the advancements in computing and information technology. So that's why. So if I say that this is the data, when you apply machine learning, its performance improves. So this is the performance. Its performance improves, but after some time, the performance gets saturated. So that's why when you have small data, we do not go for deep learning techniques. We still go for machine learning techniques. Though there are techniques like data augmentation by which you can increase the number of samples, you can increase the number of data, and then you can go for deep learning also. But in case of deep learning, which to increase the size of the data, its performance continuously increases. That is the basic difference between machine learning and deep learning. So the main purpose of such techniques, that is machine learning or deep learning, is that there are huge amount of data sets. Analyzing such huge amount of data sets manually is very difficult. It will be prone to errors. So that's why we need some automated techniques or machine learning techniques or deep learning techniques so that the classification can be done automatically. And maybe you have gone through these fundamentals in the previous class, previous lectures, that there are three types of learning. One is supervised, then we have unsupervised learning, and the third is reinforcement learning. In case of supervised learning, so let us take an example and try to understand this complete machine learning pipeline. Okay. So once we have decided that I want to go for some kind of medical data analysis. Okay, either it is lung sound analysis or it is any type of medical analysis, medical data analysis. The first step in any research is that you will identify some problem, right? Either by discussing with your supervisor or discussion with some of the experts from the field. The first step will be to decide a problem. And after deciding the problem, you will prepare a proposal, and that proposal will go to some committees for approval, right? Right. So particularly in medical field, the first committee that approves the data is ethics committee. So there is ethics committee in every institute where such type of studies are going on. It is very important that if you are collecting your own data, which involves human sample, it is very important that the first step is what? To get the approval of ethics committee, which will look upon the risks and benefits of undergoing that research by you. Okay. After getting the approval of ethics committee, now the second part will be what? So we are assuming that the uh, proposal is approved by the ethics committee. The next step will be data collection. The next step will be what? Data collection. I am assuming that I have a data of say 100 lung sounds which corresponds to asthma and 100 lung sounds which corresponds to COPD. These are two diseases which results in some breathing issues there because of the blockage of airways in the lungs. Okay, so we have COPD due to obstruction in the lung. So suppose we have 100 signals, one of COPD and one of asthma. So I'll take this example and explain you the complete machine learning pipeline. Now, after getting this data, so this data, like in our lab, we collected such data with the help of electronic stethoscope, Littmann electronic stethoscope. That is a standard electronic stethoscope, which has been cited in many research articles. So we purchased it and we used it. Now we are trying to develop a low-cost stethoscope also in our laboratory. But this study, which I'll be discussing also later at the end of later, we'll be discussing this study in the detail. This is my data. Now you may have a similar type of other data, like maybe you'll have some samples of EEG, or somebody of you might be working on images, so you'll have some medical imaging. Okay, so here for the example, I'm assuming that I have 100 samples corresponding to asthma and 100 samples corresponding to COPD. The first step in any of these studies is what? Any of the medical data analysis study is what? It is data collection. Now, sometimes we don't do data collection by ourselves. It is difficult, obviously, to collaborate with hospitals and to match your timing and everything, and the working style with doctors. It is very difficult because they are very busy. So we get data from different online resources. Okay, like there are many open repositories from where you can get the data directly. In that case, you may not need the permission of ethical committee. Okay, but if you collect your own data, then you must take the permission from ethical committee. And the first step is data collection. This data can be signal, image, it can be any clinical data, it can be any pathological data, it can be any medical data. Okay. After this, the next step in machine learning pipe is data pre-processing. Data pre-processing. So this data pre-processing basically means you have collected the data which will always have some types of noises and artifacts. Particularly in most of the biomedicals, we have some standard noises and artifacts. Okay. So for example, if I record EEG data, during the recording of EEG data, okay, if there is a blinking of eye, it will result in eye blink artifact. Okay. During the recording of EEG, if I move my hand, that will also result in some type of noise. During the recording of ECG, if there is a cough or cold, and because of that, if the chest moves, that will result in some kind of noise and artifact. During the recording of respiratory sound, which other sound will be recorded from the body? Other than lung sound or respiratory sound, which other sound will be recorded? Heart sound. That is a major issue in respiratory sounds analysis, that along with the respiratory sound, that heart sound will also be recorded. And along with that, because we are recording sound, we'll be using some type of microphone to record the sound. So it will also record some of the surrounding noises. If fan is moving or if some other kind of noise is coming, that will also be recorded. So that's why this data pre-processing is very important. Either you are doing ECG, EEG or any other study, this data pre-processing is nothing but it is removal of noises and artifacts. Now, nowadays, other than this removal of noise and artifacts, there are other things also people are doing. As I told you that getting a medical data is not very easy, correct? So what can I do? Sometimes what people do, suppose I have 25 subjects having COPD. I have 25 subjects having asthma. But how many I need? 100 samples. So what I can do, I can record long trials, lung sound signals. Say I record it for say 15 minutes. Okay, I record it for 15 minutes. And then later I can segment it for 1 minute. So from one subject, I can get 15 samples. This is also nowadays people are doing to increase the number of samples. Okay, that also comes under pre-processing. So whatever you do with the data in the initial steps, all these come under what? Pre-processing. EEG also, it is very difficult to get the data because it takes long time to record the EEG. Setup itself will take half an hour. Just preparing the setup itself will take half an hour. Okay. So after recording the EEG, sometimes what we can do, we can, if I have recorded 5-minute EEG, 10-minute EEG, we can break it into say 1 minute, 1 minute or 2 minutes, 2 minutes, so that we can increase the number of samples. Okay, that also comes under data pre-processing. In data pre-processing, what we do, we have removed the noise, we remove artifact, and then we also do some kind of, like for example, data segmentation, as I just told you, dividing the whole signal into small segments so that number of samples can be increased. Now, in machine learning pipeline, once the data is pre-processed, after pre-processing, now the next step is feature extraction. Next step is feature extraction. Okay, so we'll come to feature extraction later on. I'll come to some slides, then we'll start feature extraction. So I hope you understood so in supervised learning, what happened? Now, we had 100 asthma and 100 COPD. Okay. If you know that, so we have 200 samples, and along with these 200 samples, we have one more additional variable that is available with us. That variable is class. That variable is class. Class means I know that out of these 200 samples, which sample is asthma and which sample is COPD. That is also an information that is very important. If you want to conduct any study, this information is very important. It will be provided by the concerned clinician or some medical technician. Okay, so this along with this 200 samples of data, 200 lung sounds, additionally you have what? Class. Class is very important. So class is say 1 and 0, where 1 corresponds to asthma and 0 corresponds to COPD, or -1, 1, where -1 will correspond asthma and 1 will correspond COPD. This class is available to you. In supervised learning, the data that is available and the class, they are used to develop the model. Together they are used to train the model. Okay, so the machine learning learns from the training data and labels and make prediction. So here both are available. One is training data and the second is what? Labels. These labels is nothing but these class. When both labels and data they are available, we generally go for supervised learning. Okay, like if I want to make you learn, I will say this is what? Whiteboard marker. So I have given you the data also. This is the data. And then I have told you the label that this is whiteboard marker. This is how we have learned from our childhood. We had both input as well as output. So the same pattern is followed here in supervised learning. You have both input and output. Here I have both input and output. I have samples as well as I have what? Its label. When both are available, we go for supervised learning. In unsupervised learning, generally you have a data in which label is not with us, label is not present with us. In such situations, we go for unsupervised learning. Okay, so what will happen in unsupervised learning? I have given you some data, then I ask you to categorize it in 3 groups. Randomly, I will say just divide them these. I give you some chocolates and I ask you to divide these chocolates into 3 groups. Then how you will divide? You will see that what is the similarity and differences among the chocolates by your own common sense, by your own logic, right? Okay, that these wrappers are red in color, let us make them in one group. These wrappers are blue in color, let us make them in one group. And these are yellow in color, let us make them in one group. So there the label is not available, but by using some kind of information or characteristics, we automatically segment it into different groups, different clusters. We call it as clusters. Okay. And the third is reinforcement learning, which is kind of semi-supervised learning. This reinforcement learning is kind of semi-supervised, in which though the label is still not available, but we have some type of rewarding system which informs the model that whether the model is training or learning in the right direction or wrong direction. So we give some type of reward, some kind of scoring system, so that with the help of that scoring system, model understands that it is going in right direction or wrong direction. So these 3 are the main types of machine learning techniques: artificial neural network, support vector machine, naive-Bayes classifier, linear discriminant, and classifier are there, which come under supervised learning. Deep learning, LSTM. In unsupervised learning, mostly the clustering techniques, they come under unsupervised learning. Like for example, KNN. Okay, K means clustering, fuzzy C means clustering. They all come under unsupervised learning. Okay, and this reinforcement learning actually, okay, it is not there. So there are some techniques like, for example, Markov model, hidden Markov model. Okay, that come under this reinforcement learning, where there is some kind of scoring system which scores the model, and with the help of that, the model understands whether they are going in right direction or wrong direction. Also, in machine learning, there are 2 terms which are used. One is classification and other is regression. In classification, you are simply saying yes or no, asthma or COPD, normal or diseased. That is classification. But in regression or prediction, it's also called prediction. In prediction, what we do, instead of simply saying yes or no, we are predicting some value. Like for example, here the example is given, predicting student marks in percentage on the basis of his performance in, say, previous semester. Say predicting student performance in first year of the BTech course by taking as input all the previous marks, say from class 5 to class 12. So on the basis of some type of data, you want to predict what is the new data, like climate forecasting or something, where we simply don't say yes or no. Okay, this is the difference between classification and regression. So this already we have taken. Now before going to this neural network, I will again come back here. Now we have done with data processing. In feature extraction is a part of machine learning, not deep learning. Okay. In feature extraction, now we'll extract some variables from the lung sounds. We'll not take the whole lung sound together to the machine learning model. We'll extract some features from the lung sounds. Like for example, a very simple feature is mean of the lung sound. These lung sound are these lung sounds are available in which form? Not continuous, discrete form. They are available, or rather, I should, instead of saying discrete, I would say they are available in sampled form. We have a row of numbers. We have a row of numbers. The lung sounds, when discretized, will give me row of some numbers. Okay. So the feature extraction means simply, now you want to extract some features from this data. A very simple feature is mean. It can be entropy, can be skewness. These are very simple features. Nowadays, there are very advanced feature extraction techniques. Kurtosis. These are some of the statistical features which can be extracted from lung sound or EEG or any kind of signal. These are very basic features. Nowadays, very advanced feature extraction techniques are available. So how these features are calculated? You can do some programming in MATLAB, Python. So I'll just give example. Suppose I want to calculate entropy and my lung sound, our discrete data I am assuming like this 2, 3, 4, 5, 2, 7, 2, something like this. Okay. So the formula of entropy is what? Summation of minus P log P. So those from electronics background might be knowing this formula. I'm not sure about computer science and other backgrounds. Okay, this is the simple formula of entropy minus P log P. These equations are given in literature. There is nothing new in them. Okay, like mean will have a simple formula, sum of all the samples upon total number of samples. That is a very basic formula you all might be. Okay. Similarly, formula of entropy is minus P log P, where P is the probability of occurrence of a particular value in the row. So for example, if I calculate P2, what it will be? It occurs 3 times. So 3 by 1, 2, 3, 4, 5, 6, 7, 8. So this is P2. Similarly, calculate P3, P4, P5, and then put it in this formula. Minus P log P. So minus 3 by 8 log 3 by 8. Okay. What is P3 here? 1, 2. 2 by 8. So this was minus 3 by 8 log 3 by 8 minus log 2 by 8 log 2 by 8 minus 5 by 8 log 5 by 8. In this way, we proceed and we add all those to get the entropy. Entropy is measurement of uncertainty. If the amplitude values will change very frequently, it is assumed that entropy will be high. Okay. So this step is called feature extraction. I am assuming that then we also take standard deviation. So we had how many lung sounds? 200. From these 200 lung sounds, I have extracted how many features? 5 features. So my table will be what? 200 into 5. My table will be now 200 into 5, 200 rows and 5 columns. There will be one additional column. So I'm making it 6, and that additional column will be of label. Because I'm talking about supervised learning. So that additional column will be about what? Label. So I have a new table of how much? 200 into 6. Okay. This data after feature extraction to the next step. The next step is you can do either statistical significance analysis or feature selection. Those who are PhD students and they are working in this for their first year, second year, and they want to do signal analysis. And if you want to apply machine learning, then these steps will be common to all of you. Only that you have to see what are the new techniques under a particular step. Okay. Now, statistical significance analysis means, so I have a table of size 200 into 6. I have extracted 6 features. It is very rare that we extract so much less features. We may extract 100 features, 200 features, 1000 features. So many feature extraction techniques are available. You can extract many features. Can you all see this? I'm writing very small now. Why you didn't tell me? Now I just realized that some people might know, it might not be visible to people. See, you can interrupt me at any time and you can ask me any question, or you can, like, you should have told me that you can't see. Okay, or you can come forward maybe. There is so much space in forward, in the front. You all can see that. Okay. So I was telling that we have a table size of how much? 200 into 6. Forget about this 6 at present. We have how many features we extracted? 200 into 5. Okay. Statistical significance analysis is an approach to determine that whatever features we extracted, here it is 5, but actually it will be 100, 200, 300. Okay. So whatever features we extracted, are they really significant or not? Like, for example, if I want to classify apple with orange, shape will not be a good feature. I may extract it, but it may not be statistically significant. So some features may be good and some features may be, but when I say apple and orange, it is very much familiar to me. But when I say lung sounds corresponding to asthma and COPD, I'm not familiar with that. So that's why I will extract all the features and later check which feature is more significant and which feature is less significant. Now to check this statistical significance, we first do normality analysis. We all know what is normal distribution. There are different distributions of data, right? Normal distribution, Gaussian distribution, uniform distribution, non-uniform distribution. Okay. So what is normal distribution? Normal distribution is distribution type in which the data is normally distributed, means it is Gaussian only. It's kind of like this Gaussian curve. Okay, the data is distributed like that. If the data is normally distributed, we use t-test. We use t-test, independent t-test. And if the data is not normally distributed, we generally go for Mann-Whitney U-test. Mann-Whitney U-test. These things can be easily done using Excel or some specialized softwares like SPSS. Okay. So what is the purpose of doing this statistical significance test? The output of this will be that whether a particular feature is really able to differentiate asthma and COPD lung count or not. What we do in this statistical significance analysis is there is something called as p-value, which is called significance value. If this p-value is less than equal to 0.05, then we say a feature is significant. If the p-value for a particular feature is greater than 0.05, we say that feature is. अब ये 0.05 कहाँ से आया? This comes from again an assumption which we make at the beginning of statistical significance analysis, which is called confidence interval. If you take confidence interval to be 95%, then p-value will be, the cutoff for p-value will be p equal to 0.05. If I take it to be 99%, the cutoff will be 0.01. So higher is the confidence interval, lesser will be the cutoff, more accurate will be the model. Because if I take p-value less than 0.01, so I'm putting more restrictions. That if for a particular feature, the p-value is less than 0.01, then only I'll consider it as a significant feature. I'm putting more restriction in that. Okay. So the purpose of statistical significance analysis is to find those features out of 1,000 features or 100 features which were significant. So I may reduce to say 40 from 100. Here we have started only 5 features, but in real time scenario, suppose we extract 100 features, you may reduce to how much? 5 out of 100. Suppose only 40 are significant. Only 40. So I will go forward with only those 40. Okay. Other than that, in machine learning, so this is actually not the part of machine learning, but we use it. But the main machine learning part, the main term which is used is what? Feature selection. Feature selection is also the process to select the most relevant features which can differentiate between two lung sounds, asthma and COPD. Okay. So what happens in feature selection is, So what we can do is, like what we do usually when we do feature selection, it's very difficult to know exactly. Uh, so feature selection will give, with the help of some criteria, feature selection will give you that these features are there. But you may have a second check that whether these features are also statistically significant. So why we use it in the machine learning pipeline is that it just provides us a supplement information. It's not necessary. It's not compulsory. You may go directly with feature selection and move forward. Yes, because sometimes what happens now in feature selection, suppose out of 100 you got 50 features at good features. But if you still want to reduce the model complexity, so again you can check that out of 50, how many are statistically significant. They may reduce the list even to smaller, or vice versa. You got 60 as statistically significant, but feature selection may give you 30 only. Okay, so just we do this thing just to reduce the complexity of the model. Okay, now in feature selection, so I answered your question, right? So in feature selection, what we do, and discuss little bit more about feature selection. Feature selection. I told you that the purpose of feature selection is again the same, to reduce the number of features. We had so many features, like 100 features or 1000 features. We want to reduce the number of features. So feature selection is broadly classified into two types. One is called filter method. The other is called wrapper method. Other is called wrapper method. In filter method, what happens? We decide some kind of criteria. Like for example, in a class of 100 students, if I want to find top 10, best 10 students. So how will find? I'll use some criteria, say CPI. CPI in the previous, percentage of marks in the previous semester. That can be criteria. Or the students who are very good in extracurricular activities. That can be one criteria. There can be many criteria. With the help of a particular criteria, I will decide, I will rank all the features. Here I have how many features? 6 or 5. But suppose there are 100. See, when I extract only 5 features, feature selection is not required actually. Why to reduce? Because we have only 5 features. But suppose we have 100 features, we will do feature selection. So in filter method, what happens? With the help of some criteria, all the features are ranked. There are 100 features. Say feature Say feature 1, feature 2, feature 3, feature 4. I will rank all that. So all the features are ranked. So this is feature number 1, feature. So suppose this feature, the first feature got ranked 5, the second got ranked 3. If there are 5 features, just assume 5. This got rank of 2, this got rank of 1, and this got rank of 4. So in filter method, by using some criteria, so what criteria? For example, there is one criteria called as Gini index. There is one criteria called as information gain. These are some criteria. Okay. So by using some type of criteria, all the features will be ranked. There are 100 features, you rank all the 100 features, then take top 10, top 20, whatever you want to take. Again, there is no golden rule to select ki top 20 hi lena hai, ki top 10 lena hai. You have to do multiple experiments and check that whether you're getting highest accuracy with top 10 or top 15 or top 20 or like that. You can do multiple experiments and check. Okay, so this is what we do in filter method. Wrapper method, instead of ranking the features, what we do, we try to find the best subset of features. Now, what is that best subset? In a class of 100 students, I want the best group of students who can together perform best. I don't want individual performances. I don't want to check individual performances. I want to find the best group in the class, group of say 10 students, okay, who together perform. When they're together with each other, they perform very good. So in wrapper method, instead of ranking all the features, we try to find out the best subset or group of features. So how we can do? Again, one technique I'll tell you. Suppose I use only F1. We had 100 features. Let us assume we have 5 features. So I'll first use what? F1 and check the accuracy of the model. Then I'll take F2. I'll add F2 in it. Again, I'll check the performance. Suppose the performance increases, I will keep F2. Again, I'll take F3. Okay. Suppose the performance decreases, so F3 will not go forward. Then I'll take F4. Performance increases, it will be there in the group. Then F5. Performance decreases, so F5 will not be added in the group, and my final subset will be F1, F2, F4 in the first round. In the second round, what we'll do? We'll now start with F2 and repeat the same process. F2, F1, F2, F1, F3, F2, F1, F3, F4. Then I'll start with F3. Then I'll start with F4. Then I'll start with F5. Repeat the same process. Are you getting me? And finally, whichever group gave the maximum accuracy, that will be selected. So for 5 features, it is very easy. We can do it even manually also. But just remember, imagine that when we have 100 features or 200 features or 1000 features, how much time it will take. So wrapper method gives you the best subset, but it is computationally very expensive. It will take a lot of computational time. On the other hand, filter method is a simple method compared to that. But in filter method, we'll not be able to know exactly how much features should we take. Should we take top 5 or top 10 or top 15 or what? Okay. These are the two methods. By using any one method, you can do feature selection. Once you are ready with your features, yeah. So suppose out of 5 features, our table size was what? 200 into 6, including label. Now it is suppose reduced to 200 into 4. Means out of 5, I selected only 3 features for which were very significant. I eliminated 2 features. Though again, I remind you, for 5 features, feature selection is not required. You should take all the 5. But however, if some feature is really statistically insignificant, we can remove. Okay, I have now 200 into 4 after feature selection. Now the next step after feature selection is, we have done feature selection. The next step is training and testing of the model. Training and testing of the model. Now what is model here? So model can be artificial neural network, the most fundamental one. Okay, so let us little bit talk here. Model can be artificial neural network, it can be code vector machine, any other which I told you also that so many models are there. Can be any model, but before going to that model, we must divide our data from training to testing. Again, to divide the data into training and testing, we have different rules, which I will call as data division rules. Data division rules. The first data division rule is holdout method. The first data division rule is what? Holdout method. In holdout method, what you do, had 200 samples total. Okay, we had 200 samples. From that 200 samples, randomly, so randomly word is important here. Randomly, we take some percentage for training and some for testing. It is random. Out of 200 samples, randomly, some will go in training folder, some will go in testing. Now, how much it will be the ratio, that depends on the user. Again, there is no golden rule, but generally we use 30% for testing and 70% for training. There is no golden rule for that. So generally what happens, like if I'm working in lung sounds, I will see what previous researchers have used, so that we can do comparison with our work. I know. So I'm just assuming that we have 70% for training and 30% for testing, or 80% for training and 20% of So that's why it is called hold out. We randomly hold out some percentage of data for testing. The problem with the holdout method is that it is very simple method because randomly it is selected. But the problem is that, see, when you collect data, data will include both good samples and bad samples. So data will not always be very clean and very good. It will include some faulty samples. Like for example, in a class of 100 students, randomly take 10 students. It may be possible that all the 10 are either very excellent students or all the 10 are very bad students. Anything can happen. But we want the mixture so that model can be trained with good data. Like if a teacher is teaching in a class, he or she should solve both easy problems and tough problems with the students. Similarly, when I want to make the model learn, I want to present good samples as well as bad samples. But if you do hold out and take randomly, the problem will be that the training data may not consist of some good samples or some bad samples, which we needed. Okay, so that problem can be solved by using a process which is called as repeated holdout. Repeated holdout. In repeated holdout, what happens? The same process is repeated 100 times or 50 times. It depends on you. Again, there is no golden rule. So if I repeat the same process 100 times, there will be a chance that every time when I randomly select the samples, obviously when you select randomly, they will not be same always. So sometimes good samples will come, sometimes bad samples will also come. Okay. So, but still there is a chance that few samples may not be selected any time in training or testing. Maybe then also there is a chance now because every time we are doing it randomly. If I'm taking a 10 students randomly from the class, even if I repeat it 100 times, there may be a possibility that 5 students were never selected for training. There is a chance. Therefore, to address this issue, the most accepted way in machine learning field is for data division is k-fold cross validation. K-fold cross validation. In k-fold cross validation, we divide the whole data into 10 groups, assuming that k equal to 10. But you can take k equal to 5 also. But if the data size is sufficiently good, we can take k equal to 10. If k equal to 10, there will the whole data set will be divided into how many groups? 10 groups. Each group will contain how much? 20 samples. 20 samples. Okay. So asthma will take 10 from asthma and 10 from COPD and form one group, G1. Then similarly, G2, G3, G4 up to G10. And then what will happen? 9 groups go for training and 1 group go for testing in the first round. In the first round, 9 will go in training and 1 will go in testing. In second round, so for example, G1 go for testing, remaining 9 go for training. In the second round, G2 goes for testing, remaining go for training. Third round, G3 goes for testing, remaining go for training. And so on. So how many rounds will be there? 10 K rounds. K, जितना भी K का value लेंगे, उतना rounds will be there. And then all the results are averaged out. All the results are, अभी results कैसे निकालते हैं अभी आगे देखेंगे. Whatever results we get, that is averaged out for the 10 round. This is how you divide the data into training and testing. Another data division protocol, which is generally used when you have less number of subjects or the number of samples is less. Like I have performed some easy experiment only on say 15 subjects. Then I can go for this data division problem, the data division protocol. It is called leave one subject out. Data division. Leave one subject out, data division. It is nothing but it is k-fold only. It is nothing but a k-fold only. It is a special case of k-fold with k equal to 1. अब k equal to 1 में क्या होगा? I have how many subjects? 15. 14 will go in training, 1 will go in testing. Leave one out, only one out. Out of 15, leave one subject out. So out of 15, 1 will go in testing, remaining 14 in training. Then the second will go in testing, remaining 14 in training. So this will go how many times? 15 times. There are 15 samples, 15 subjects. One subject will be used for testing, remaining 14 will be used for training. So this will go how many times? 15 times. And again, the results are averaged out. So when the number of samples are less, you can go for leave one subject out data division protocol. Once we have divided our data into training and testing, next, training the model. This is just a data division. After that, we have to do training and test. So now, no, please. Yes. See, what I told is that these both are same. Only that when you have less number of samples, it will be equal to 1. But I can use k equal to 2, k equal to 3, that depends on me. But the most acceptable way, when you have higher data size, go for k equal to 10 or k equal to 5. Lower data size, go for k equal to 1. But if you take k equal to 2 for say large data size, it will take more time. Okay, so we have to decide the value of k such that the time complexity should also be lower. The time requirement should also be lower, and our purpose is also. So again, there is no golden rule that whether when we can take k equal to 2 or 3 or 4. But yes, we can take k equal to 2 also. So you have to write two-fold cross validation. What? So that's what I told you. Depending upon the size of your sample, if the size of the sample is say 40, for a subject are 40, will not go for one fold. It will take lot of time. So we generally if we have 40, I may go for say 4-fold or 5. If I take 5-fold, how many groups will be there? 5 8 the 40. So I'll get that 8 groups. So that's what I'm telling. There is no golden rule. I can report my study in the research for multiple fold. You can report for 5-fold, 4-fold, 10-fold also. Like if I have 40, I can use 10-fold also. 10-fold means how many will be there in each? 4. 4 times the 40. That also I can do. So that is in machine learning, one problem is there that there is no golden rule to select few things. So suppose I'm working in respiratory sound and I'm working on some online data available in public repository. If some data is there in public repository, it means that people might have worked on that. See their papers and see what they did, so that we can use the same rule for comparison purpose. Maybe my model is different, but if for data division they use 3-fold, I can also use 3-fold just to compare my study with theirs. But there is no golden rule to select kitna fold lena. But the general rule is that you have say very less number of samples, 15 and 20. We should report 1-fold data division. And along with that, we can report 5-fold also. There is no issue. But if we have higher number of samples, we generally go for, obviously, if we have say 200 samples, this will take a lot of time. Go for 10-fold or 5. Okay. Now, we are talking about number of subjects. Number of samples also means number of subjects only. But sometimes what happens? From one subject, we can take 5 samples also. Number of samples means number of signals. The signal may be 1 channel, 2 channels, 10 channels, 16 channels. Like in EEG, one signal means 16 channels. One sample means 16 channels or 32 channels, depending upon what device we are using. Okay. So in any of the case, the same rules applies. It depends on number of samples, not the number of channels. Okay, number of samples. The number of samples are high, we generally go for 10. Everywhere I'm saying generally. Okay, because there is no golden rule, but whatever has been reported for higher number of samples, we can go for 10. Now, once you are done with training data and testing data, now we have to train them. So now I want to explain you what is training with the help of a topic called as artificial neural. Might be knowing about this topic, but I simply wanted to explain you about how the training thing takes place. Okay. I'll keep this and directly come to artificial. Whether ANN is covered here? Okay. So this artificial neural network theory is based on biological neural network theory. Biological neural network theory means how our brain functions. The, the functioning of the brain, the functioning of the brain is picked to make artificial neural network. Okay. The brain consists of millions of neurons. They are not artificial neurons, they are biological neurons. Okay. These neurons are highly interconnected with each other. There are multiple neurons. Okay. And these neurons are highly interconnected with each other. Means every neuron is connected with every other neuron. They are highly massively parallelly connected, interconnected to each other. Okay. So what this neuron is, first let us see. So this is a diagram of neuron. We have the cell. Center is called cell body. This is center is called nucleus, but this is called cell. And the function of this cell is that it receives information from multiple neurons. It receives information from multiple neurons. So the function of this cell is to add all the inputs which it receives from the surrounding neurons. Okay. So we have this cell body. We have this cell body. Cell body is one of the parts of neuron. What is its function? Sums all the inputs. Because there are multiple neurons, millions of neurons. Every neuron receives information from other neurons also. Okay. So, and then other than that, we have axon. This part is called axon. The function of the axon is what? It transmits signals to other cells. So I have multiple cells. This is the cell body which adds all the input. And then through this connection, which we are calling it as axon, the information is transmitted from one cell to another cell or one neuron to another neuron. Okay. And these dendrites, these are called dendrites. The function of these dendrites is to receive inputs. If this is the cell, the outgoing channels are called axon and the incoming channels are called dendrites. Dendrites are used to receive information. Okay, means these axon terminals are actually connected to these dendrites. Axon terminals are sending the information. Dendrites of other neurons will be connected to these axon terminals. So this is a very simple figure, and from this you understand what are the three main things here. One is the cell body which adds all the inputs which are received from the surrounding. The second is that there are some channels which passes the information to other cells, and then third, there are some channels which receives the information from other cells. This is how neuron functions. Okay, and when it receives the information from other cells, if their summation is sufficiently higher, we say neuron gets fired. Like if I'm walking in a gallery and if my friend passes, like just crosses me, my friend crosses me, then there will be some neuronal activity. I will recognize it. I'll say hi, hello. Okay. But if somebody unknown passes or crosses me, there will be no firing of neuron. I'll simply go. This is what is meaning of firing and not firing. Okay. Whatever we react, whatever we act, it is because of functioning of firing of these neurons. The same concept is now mimicked to develop something called as artificial neural network. This is the diagram, very simple diagram of artificial neural network. Try to match both. So here we have a summing junction. Here we have a summing junction, which is similar to what? Cell body. Okay. We have a summing junction, which is equivalent to cell body. And these are the different inputs which are coming from dendrite. Correct? Different inputs which are coming from dendrite, they are added. And if they are sufficiently higher, now to determine if it is sufficiently higher, we have something called as activation function. In a very crude language, we can say it is a transfer function. It is a transfer. It will decide a threshold that if some of all the inputs is higher than this value, it is higher than this particular value, the neuron will get fired. It is a kind of decision maker that whether VK is sufficiently higher or not. Depending upon that, the output will be either fired or not fired, 1 or 0. And then we have something else here which is called as W1, W2, W3, W4, which are called weights. These are called what? Weights. Because the information, all the information, when I'm passing through a gallery, I'm receiving many informations, right? Somebody is going in first floor, somebody is going in second floor, somebody is crossing me, somebody is teaching in class. So many inputs are coming, but the weight of all the inputs will be different. The weight of all the inputs will be, weight means the strength of all the inputs will be different. These are the strengths of all the inputs. Okay. So when I say learning or training, training means learning of the model, training of the model. Training of the model simply means, so what, just try to understand how many features I have? 4. Here we had how many? 3. 4. We were left with 3. Sorry, one is label. So we will just imagine we have x1, x2, x3 that we give to the model. Let their weights initially be 1, 0, 1. Any weight we can give. That is random. The first step is random. So I give 1, 0, 1. It will be added. It will be added. Then I'll get some output. What is my table size? 200 into 4. 200 into 3 features and 1 is the label. Just try to imagine in your brain now. First, I give the first row. First row means how many features? 3 features. In our case, how many features? 3 features. I'll give that, and along with that, I also give output, the label in supervised learning. So I gave 3 features. I got some output, and I will match whether it is equal to my label or not. If it is not equal, these weights have to be updated such that the input matches the output. Because I'm doing supervised learning, so my input and output should match. That that is the way that my model will train. Like we teach the student that see this is the apple and this is the orange, and then we take an exam whether it is matching or not. His answer is matching or not. If it matches, you will say the student has learned. Similarly, here you give the inputs, you get the output, and you check whether the output which I am getting is equal to or same as my actual output or not. And if it is same as the actual output, the weights will not be updated. But if it differs, these weights need to be updated such that we should get the same output what we desired. Did you understood what is learning here? Obviously, if you change the weight, it means that you are changing the strength of the information, so that the output will be different. The reaction will be different. Yes, yes. Okay. But this is not the end. We did only for first sample. Now we'll give. So first sample के लिए हमने fit कर दिया. If this is the input, I am getting the output which I wanted. Now we will give second sample. The weight which you fixed for first sample, that weight will be used for second sample. And then again we will check. इस second sample में जो output आना था वो आ रहा है कि नहीं? अगर नहीं आ रहा तो weight फिर update. फिर third sample देंगे, fourth sample देंगे. The aim is to find the value of weight such that for all the training input, the required outputs should be obtained. Just imagine how much complex it is. It means that you may match the weight for first sample, but that may not be true for second sample. Again, you match it for second, but that may not be true for third. So training means what? Continuously updating these weights, and then to reach up to a weight such that that weight is applicable to all the inputs, all the samples. That's why training takes a lot of time. Sometimes, obviously, it is possible that 100% accuracy in training is not obtained. So that's why we sometimes find training accuracy also. It may not be 100%, it may be 98, 97, 90. This is what we call it as training. So this I explained you already, that we multiply all the inputs with weights. This is the input, W is the weight, we multiply and then we add on. So x1 into W1 plus x2 into W2 plus x3 into W3. We add on and then we get UK. It should be VK actually. VK, this VK. And after getting this VK, pass it through a transfer function to get the final output. Okay. The transfer functions can be like this. So here you see, if the sum of this input Vk is greater than t, the output will be 1. Otherwise, the output will be 0. Here, if it is greater than 0, the output will be 1. If it is less than 0, the output will be minus 1. It's Vk. Here, it is not a linear, it is not directly mapped. Depending upon the value of input, wherever it comes, a particular output will be obtained. It's not always +1 or 0. It may be some decimal output also. Okay, so these are some examples of transfer functions. We can take break. I was also thinking.
Yes.
बहुत लंबा होने से फिर
10-minute break. चलिए तो बड़ा सलाद है सलाद बहुत
हाँ खुला है।
एक्टिविटी बना So this I have already told you the process. The process is that first you have to initialize all the weights randomly, W0 and W1 and W2n. So first you have to initialize all the weights. Okay. After the initialization, you will add them. The summing junction will add them. Okay. This is nothing but into W1 plus H2 into W2. Summer will add all the inputs and then this input will be passed through a transfer function. So this is the transfer function, signum function. If the input is greater than equal to 0, the output should be 1. If it is less than 0, the output should be -1. Okay. So this we have already discussed. And once you get the whatever output you get, now you compare it with the actual output. So you calculate the error. So Vn is the sum of all the inputs and Yn is the actual response. Dn is the desired response which I wanted. Yn is the response of the model, actual response of the model. We calculate their difference. So we get the error. Correct? In this supervised learning algorithm, we had 200 samples. How many features? 3 features and 1 label. I gave the first sample. के जो 3 फीचर थे, पहले सैंपल के जो 3 फीचर थे वो मॉडल में गया। मॉडल में जाने के बाद क्या हुआ? I first initialize the weights. Okay. Then what happened? X1 into first weight, X2 into second weight, X3 into third weight. Correct? Then I did the summation. After getting the summation, I got some output. If that output is greater than or equal to 0, the output of the model is 1. Otherwise, it is -1. After getting this output, now I will compare it with the desired output. Now I compare it with the desired output. If both of them are same, the error will be 0. The error will be 0. And if they are not same, there will be some error. There will be some error. So if there is some error, we'll have to update the weight. We will have to update the weight. Now to update the weight, we have many rules. One rule is this. New weight to old weight. Now see, whatever I'm talking in a very fundamental way. Really want to work in this area, you'll have to read some good books. Okay, so that you will know what are the different rules for updating the weights. So one rule is this: new weight is equal to old weight, which I assumed randomly initially. Theta is the learning rate. Theta is called it is a training parameter, but it is also called learning rate. If eta is very less, the learning process will go slowly. If eta is very large, the learning process will go faster. So here we are taking that eta also, and then the error dn minus yn into input. It's a very simple mathematical equation. So new weight is nothing but the old weight plus error. Just for a moment, even you can neglect eta. New weight is equal to old weight plus error into input. This will give you new weight. Now with this new weight, again check whether the output is coming or not. Again check whether the output is coming or not. Keep on updating these weight until what? You get a weight which classifies all the available training inputs correctly. This is called training of the model. Okay, so this is some basics about neural networks. I'll skip this, but I hope you understood that how this learning process takes place. I have taken one more example here. Assume that there are 2 classes, 3 samples and 2 features. A very simple example to understand how learning takes place. I have first sample, 2 features, 1 and the values of those features are 1 and 2. And what is the label here? 1. T means target, means label here. P2, second sample, features values are -1 and 2. What is the label here? Then P3, what is the features value? 0, -1. Label is instead of 200, only how many samples? 3 samples. I have plotted also those. First is 1, 2. So this will be 1 amplitude and this is 2. First sample comes here. Second is -1, 2. This is -1. Y is 2. Second sample comes here. Third is 0, -1. So this is 0. -1 means here Y. This is my third sample. Sample with 0 class is blank circle, and the sample with 1 class is filled circle. Okay. This is a very simple problem just to understand the concept. Now you see here you can easily draw a line to separate the 2 classes. Can you? Correct? Such types of problems are called linearly separable problems. Most of the real world problems are non-linearly separable. Okay, like for example, you all know what is XOR gate? What is the output of XOR gate? Output and input was XY and output 0, 0, 0, 1, 1, 0, 1, 1. What is the output for 0, 0? 0 or 1? Then here 1 and 0. Let us plot it. For 0, 0 input, I am getting 0. 0 I keep blank. This is 0, 0, right? X is also 0, Y is also 0. What about 0, 1? X is 0, but Y is 1. The output is 1. Correct? 1, 0. X is 1. Y is 0. The output is 1. Then both 1. Here. X is also 1. Y is also 1. The output is 0. Just assume that it is a two-class problem. Two-class problem means 0 and 1 is the output, and these are the inputs. How many features are there? 2 features, 1 label. I plotted it here. Now, can you draw the straight line to differentiate both the classes? This is not possible, right? We will have to do something, right? Such type of problems are called non-linearly separable problems. Most of the real-world problems are actually non-linearly separable. Okay. Now coming back to the question, you understood this question first of all. How many samples you have? 3 only. P1, P2, P3. How many features? 2. And how many classes? 2. 0 and 1. This will be the neural network architecture for that. Only 2 input, only 2 weights, addition, net output of summer, a summing junction, passed through a transfer function, and we get the actual output of the model. This is the neural network architecture for this problem. So let us take the random weights first. This is the initial weight. This is the initial weight which I am taking just randomly. 1 and minus 0.8. Two weights hai na? There are 2 weights. Taking this randomly. 1 and minus 0.8. Now calculate the model output. So what will be the model output? What is your first input? 1 and 2. So 1 into 1 minus 2 into 0.8. Read out. You have to do x1 into w1 plus x2 into w2. Correct? Product of these two. This is the weight and that is the first input. I multiply them. Whatever I'll get, that will pass through this transfer function. The transfer function used here is what? Hardly. Hardly means greater than 0. This I am getting minus 0.6. So for negative, the output is 0, and for positive, the output is 1. Here, after multiplying and adding, we get minus 0.6. Because of the transfer function we use, we get output to be 0. But चाहिए क्या था? 1. Are they matching? No. So update the weight. Update the weight. Now there is another weight update rule which is very simple, which I have taken for this example. Calculate the error t minus a. What is the t? T means target. Target was 1 minus 0. So 1 minus 0 will be 1. Error will be how much? 1. If error is 1, new weight is equal to old weight plus input. I am taking that eta equal to 1. Okay. New weight is equal to old weight plus input. Do that. New weight equal to old weight. What was the old weight? 1 minus 0.8. Correct? 1 minus 0.8 is the old weight plus P1 is the input. P1 was the input. So you got this new weight. Now if you use this weight for the first input, you will get the desired output. But now we have to check it for the second. So use the same weight and apply it for P2. What output you got? Using the same process. What output you got? 1. Whether it is desired output? No, it was 0. For the second case, it was 0. Correct? Again, you have to update the weight. This process goes on until we find a weight that satisfies P1 as well as P3. P1 के लिए T1 ही लाना है, P2 के लिए लाना है, और P3 के लिए लाना है. ऐसा एक weight finally, if you keep on repeating these steps, after 5, 6 or maybe 7 steps, you will find the answer. You can do it by yourself. I've done 2 rounds. You have to do it. Again, you will update the weight here. After getting the weight, you will check it for P3. Then again, if you get the, suppose this matches, means the error is 0. Suppose the error is 0. So what will you do? There will be no weight update. So same weight will be carried for the next input. Okay. This is mathematically how we do training. This is what is called as actually training. Training means it's nothing but the updation of the weights of the neural network. Okay, by giving multiple inputs and outputs. Finally, once the model is trained, you test the model, and in testing, what you do? This I completed training. I hope you all understood. With the help of neural network, we have tried to understand what is training. Coming to testing. Now, in testing phase, how many samples we have for testing? So let us take out of 200, I used say 80%. 80%. How much it will be? 160 for training. Remaining is 40 for testing. Now these 40 inputs will go to that same neural network. Okay, without label, because this is testing, so label will not be given. This will go to the same neural network model in the previous slide, and for all the 40 samples, output will be calculated. For all the 40 samples, be calculated. I'm saying first sample, second, third, up to how many? 40. What was the target output? And what was the actual model output? Suppose the model output is like 1, 0, 0, something like that. Okay. The actual target output is already known to you. You get two columns like this. You get two columns like this. Is clear to everyone? ये टेबल कैसे आया समझ में आया सबको? आपने ट्रेनिंग किया. ट्रेनिंग करने के बाद the next step is what? Testing. How many samples were left for testing? 40. Those 40 samples will be again given to the same neural network. Same neural network, and then you will calculate the output. But this time, this output will not be compared with the desired output. Why? Because we are doing testing. But this output, whatever we obtain, will be written in column. Then desired output is written in another column. Now you have to compare this. So comparing these two manually will take a lot of time, because here only 40 samples is there. But assume that sometimes you may have 1,000 samples in testing data. So comparing them is mathematically different. That's why we have something called as confusion matrix. For performance evaluation, we use confusion matrix. Why it is called confusion matrix? Because it gives you an information about how the developed model is confused, how much the developed model is confused. You have trained the model, you have tested the model. This is plotted for testing data. So this gives you the information about how much the developed model is confused in classifying and recognizing the test sample. How it is plotted? Try to understand. We have two types of input. We have two types of input: target and model output. I'll just, because I have two classes, I will draw a 2 by 2 matrix. How many classes I had? Two classes. I'll take 2 by 2 matrix. This side I am taking model output. This side I am taking target output. Okay. One side I am taking model output. The other side I am taking target output. What can be the model output? Either 0 or 1. What will be the target output? Either 0 or 1. 0 or 1 here is written as yes, no, and yes. Okay. If the target output is 0 and the model also gave it 0, we call it as true negative. Assuming that 0 is negative and 1 is positive. If the actual output, if the model output is 1 and target is also 1, we call it as true positive. If the target was what? 0, but model gave, so target is negative, but model gave positive. So this is not positive, this is false positive. It is positive, model gave positive, but it is false with that. So we call it as false positive. And this is similarly called as false negative. So how many test samples you had? 40. Sum of this PN plus CP plus FN plus FP should be 40. Like suppose I get 20 asthma and 20 COPD. Okay. Here I get 15, here I get 16, here I may get 4, and here I may get 5. The sum of all these 5 should be 40, and then you calculate these parameters like accuracy. Accuracy is total correct classification upon total. How much is correct? Tn plus Tp is correct. The accuracy will be Tn plus Tp upon sum of all. Call it as accuracy. Sensitivity is what? Sensitivity is total number of correctly classified positive samples. Positive samples was correctly classified positive samples is how much? Sorry, TP. TP upon total number of positive kitna tha? 20. So TP upon 20 will be what? Sensitivity. Tn upon 20 will be specificity. Total number of correctly classified negative samples. This is what you do when you do a machine learning analysis. You have to start from data collection and you should reach up to what? Confusion matrix. And from this confusion matrix, you can do many more analysis, like you can calculate TPP, TNP. I leave it to you for further study. And similarly, there is something called as unsupervised learning. So in unsupervised learning, what happens? Instead of doing classification, we simply group the data into different clusters because label is not available. So because the label is not available, I'll take example and I'll explain. So consider the following points xy representing what? So the first point is what? A1. What is the value of A1? 2, 10. A2, 2, 5. A3, 8, 4. So similarly, we have how many points? 8 points. Okay? How many points? 8 points. And I want to cluster them into how many groups? Yeah, there are 3 groups. When you apply A means clustering, for this E means clustering. First need to decide how many clusters I want. Here I have taken how many clusters? 3 clusters. This again, after understanding your problem, you have to decide how many. Like if I want to do brain segmentation, brain MRI segmentation, brain MRI has so many different areas, like there will be gray matter, white matter, skull area. There will be many small and large tissues. Most of them are small tissues. So sometimes K equals taken equal to 7, 8, 6. Okay. So here I have taken K equal to 3. And the first step is to decide the initial cluster. Out of these 8 points, just I will take 3 randomly, 3 initial clusters. So I take 3 clusters to be A1 first cluster, A4 as second cluster, and A7 as third cluster. Okay, randomly take 3 clusters. After taking these 3 clusters, now you calculate the distance between one individual cluster and the all other points. How many points are there? 8. How many clusters are there? 3. So calculate the distance between these clusters and all the 8 points, so that we can know what is the difference between them. To calculate this distance, you can use any distance formula like Euclidean distance you might have heard. Similarly, there is another distance formula which is called as, here I have used what? Manhattan distance. So x2 minus x1 plus y2 minus y1. A very simple formula. So see the table. What was my cluster center? 2, 10, 5, 8 and 1, 2. What are my 8 points? These are my 8 points. Just calculate the distance. What will be distance between 210 and 210? 0. What will be distance between 210 and 58? 5 minus 2 plus 8 minus 10. You have to take mod. So 5 minus 2 will be 3 and 8 minus 10 will be 2. 3 plus 2, 5. Clear? What will be the cluster distance between 1, 2 and 7, 5? 7 minus 1 will be 6. 2 minus 5 will be 3. 6 plus 3 will be 9. Whether you understood how this table is prepared? So from this table, you now know that I had this 8 points and I initially decided these 3 clusters. What is the distance between these 3 clusters and these 8 points? After getting this, so so cluster 1, first cluster point, you have to not take a threshold. You have to not take what? So first वाले cluster में कितने points आ रहे हैं इस बार? See this one, this point.
You have to, step 3 is what? Assign each data point to the same cluster. A data point is assigned to that cluster whose center is nearest to the data point.
Okay. So which one is the nearest?
You have to check that.
So obviously 8, 2, 10 is nearest to 2, 10 only because the distance is 0. 2, 5 is close to cluster 3 because this is minimum. 8, 4 is close to cluster 2. 5, 8 is close to obviously the same this one. 7, 5 is close to cluster 2. 6, 4 is again close to cluster 2. 1, 2 is close to cluster this one, and 4, 9 is close to cluster 2. In cluster 1, you only got 2, 0. In cluster 2, you got all these points. In cluster 3, you got 2 points. In this way, you do the clustering. Again, you can repeat the process again. So this is the first cluster. Find the new cluster center as follows. So you have to now find the new cluster center. Initially, you randomly took 3 cluster centers. Now you have to find again a new cluster center. How you find? You can just calculate the mean. So here there is only 1 point, no mean is required. Here you have to find mean of all these points. Here also you have to find the mean of these 2 points. In this way you will get new cluster center. Okay. So once you get the new cluster center, again do the same process. Again do the same process. Repeat this process until the change in cluster is very less. This is one first round. So you have to repeat this process until what? The center of newly performed clusters, newly obtained clusters do not change. Initially you took 3 cluster centers. Later on you updated new cluster. Difference between these 2 cluster centers in the first round and second round or second round or third round, you have to check the difference. The cluster center stops changing, you have to stop the process. This is the main requirement for this. Okay.
So everybody understood how unsupervised learning takes place? This is unsupervised learning using, this is called K-means clustering. This technique is called K-means clustering. Okay. Okay, so this, now I complete the part 1. Very fastly now I'll go to part 2. It is mostly theoretical. Introduction to biomedical signals. And then I'll come to lung sounds.
Okay. So most of those who are from electronic background or maybe some electrical related background, you all might be knowing what is signal. Signal is nothing but it is a function of one or more independent variables. Okay, so you all know what is phi t is equal to sine t. This is one signal. This is one signal where t is the independent variable and y is the dependent variable. Y depends on t. This is how we represent the signal. A signal is a function of one or more independent variables. This is a signal which is dependent on variable t. So a signal is defined like this,
and a signal is continuous or discrete. Continuous means whatever we see is continuous.
This is continuous. But when it is stored in computer, it is stored in discrete form, in a form of row or in a form of column, which includes many numbers. Okay.
So what is biosignal? Signals are originated from many different sources, like I am speaking through this microphone, to this mic, that is also a signal. But when I say biosignals, they are the variables or the signals which are obtained from the human body.
And these signals have some standard value and standard range. If it deviates from that, we call it a disorder. Call it as a disorder. Okay.
There can be wide, depending upon the nature of the signal, we can classify it into various types.
One is electrical, ECG, EMG, and galvanic skin response. Now, these electrical signals actually are result because of the electrical activities which are going inside the body. Now, inside the body, there are, what is the basic building block of the human body? Cell. These cells are surrounded by iron. Sodium ions, potassium ions, they are surrounded by iron. Inside the cell and outside the cell, there is a difference in concentration. There in the next slide. Okay, it is there. So based on the nature, so because of the electrical phenomena, we have ECG, EEG, EMG, GSR. Because of the magnetic field effects, we have MEG and MMG. Then we, because of the different mechanical movements like sound of joints or mechanical activities done by the body, any kind of movement like respiratory sound is also because of the chest, the sound produced by the lungs. So that also comes under what? Acoustical. Acoustic word itself means that it is related to sound, some kind of sound. So PCG stands for phonocardiogram. It is heart sound. Then respiration, because of the sound due to respiration is because of respiration, because of inhale and exhale, and then which is also called as lung sounds. Then there is something called as, another signal is called as PPG, photoplethysmogram. It is because of, it is measured through the process of called as optics, light. You all might have you all might be knowing now what is how PPG is measured. During COVID, everybody knows what that device is called. Pulse oximeter. What it measures? It was an optical device which measured your SpO2 level. Okay. So similarly, PPUG is also measured by an optical device which is placed either at your fingers or your toes. Okay. It is based on optical phenomena in which a light enters into the under the skin, and depending upon how much light is absorbed, the signal is generated. Okay. Absorbed and reflected. Then we have thermal, which is related to temperature, and then obviously body consists of lot of chemical signals also like SpO2 and blood glucose level. Now, how these biomedical signals are generated? I'll go a little bit faster because of the time. So we have this cell. The cell is the basic building block of our body, and there are certain ions inside the cell and outside the cell. So larger symbol means they are more inside. Smaller means they are less. Okay. So the concentration of these ions inside the cell and outside the cells are different. The ions are same, but their concentration is different. Because of the different concentration and the bond, this is the boundary of the cell. It is a semi-permeable boundary. Semi-permeable boundary means it does not allow everything to come in and it does not allow everything to go out. Because of the different concentration of these ions inside and outside of the cell, there is difference in the potential inside and outside, and this generates potential difference. This generates potential difference. It behaves like an ionic conductor, and because of the difference in ionic concentration inside and outside the cell, it generates a potential that is called as resting potential. And because inside is more negative, in the ideal state, inside is more negative than outside. So in the resting state, inside is more negative, and that's why the resting potential is how much? Minus. It is minus 90 millivolts. Now, when this cell is activated, how it can be activated? By some kind of external stimuli. Like at present, I am also activating some cells in you and me both because of the external stimuli. Because of the activation, external stimuli activation. So when we activate the cell, what happens? When you present some stimuli, what happens? This is the boundary of the cell which I have taken as a straight line. This is the boundary of the cell. When the cell is stimulated or some external voltage is applied, stimulated means some kind of external phenomena is taking place. There is something called as gates. These gates are usually closed. Nothing comes in and nothing goes out. But when the cell is stimulated, some gates are opened. And because of the opening of these gates in the boundary of the cell, again the ion exchange takes place. Initially, the resting potential was how much? Minus 90 millivolt. Now this, initially why it was minus 90 millivolt? Because negative ions were more inside. But when you stimulate the cell, what happens? These negative ions tend to go outside and some positive ions tend to come inside. So that's why the cell potential starts becoming positive. And this is a natural phenomena. This is a natural phenomena which takes place. How many of you are from electronics background? So you all might be knowing there is something called as diffusion in diodes. When a PN junction is combined, there is a flow of current, very small current, because of the process of diffusion. What happens in diffusion? Charge carriers start moving from higher concentration to lower concentration. That is a natural phenomenon. Same thing, similar type of thing is taking place here. Okay, initially there was a resting potential, but when the cell is stimulated, you can assume that the charge carriers start crossing the boundary, and therefore there is a change in resting potential. The resting potential reaches up to how much? So see, initially it was minus 70. Actually, the range of this cell potential at resting state is minus 70 to minus 9. Some books you will find minus 17, some books you will find minus. It starts from minus 70, then you give some external stimulation. So if the external stimulation is sufficient, this is the stimulation. Okay, but this external stimulus should be sufficient to increase the, it should be so much sufficient so that the ions can cross the junction, the boundary. Okay, so if the sufficient stimulus is applied, like this much is the threshold, when the voltage starts increasing, it reaches the highest value of say plus 40 volt. This is called action potential. All the signals which are generated from the body, like the PPG and everything, they are based on the same concept. Usually the cell is at resting potential. When external stimulus is given, potential starts rising. I want to record these potential, G or EMG or whatever. Okay, so potential increases. Once the stimulus is removed, again it wants to come to the same state, that is resting state, but it does not immediately comes to resting state. It takes some time, so it will go a little bit down, and again slowly it will come to resting state. It does not immediately comes to resting, comes down little bit more down. This is called refractory period. It is the time which the cell takes to come back to the resting state. Okay. So why I took this topic is that all the biomedical signals actually result from this phenomena. Cells are at rest, you give some external stimulus, cells activate and they generate some signal. Because of the exchange of ionic concentrations inside the body, they generate different signals. So we have biomechanical signals. Already we have discussed, we have bioacoustic signals like cardiac sounds, snoring, swallowing, respiratory sounds. So many different sounds are there. Okay. Particularly EEG is a signal which is non-invasive method to record electrical activity of the brain. So we just talked about there are many neurons in the brain. Many neurons in the brain. Okay. So whenever some external stimulus is given, these neurons get fired and they generate some type of signal which is recorded as EEG, electroencephalogram. Okay. It is a completely non-invasive method. That's why it is very useful. You have to just put some electrodes on the scalp and then you can record the EEG signal. Okay. And EEG is summation of excitatory and inhibitory पोस्ट सिनेप्टिक पोटेंशियल. अब बहुत तगड़ा तगड़ा टर्म है, इस पे कुछ कंफ्यूजन नहीं होना चाहिए. ये बहुत ही सिंपल सी बात है. एक पॉइंट से जब ईजी रिकॉर्ड करते हैं, सपोज आई एम रिकॉर्डिंग इट फ्रॉम दिस पॉइंट, then the recorded ईजी is not just because of this point, it is because of the summation of many nearby neurons. It is because of the activation of many those neurons. Okay, so that's why it is written here. It is the summation. EEG is not, if I'm placing the electrode here, it is not because of the electrode, the activity that is going exactly at this place. It is because of the summation of many excitatory, means those neurons which are in excited state. They are not in rest state. Okay. Excitatory means something which is giving information, signals which are going out, and inhibitory means post-synaptic. We just studied neuron now. It has an axon which gives information and it has dendrites which collects information. So that is what is meant by excitatory and inhibitory post-synaptic potential that are generated from these neurons are recorded as EEG signals. Now these EEG signals can be, so the frequency of these EEG signals is 0.1 to 100. Just imagine that it is so less frequency and generally we analyze 0.1 to say 80 hertz or 70. It is a very low frequency. most of the biomedical signals are very low. Okay, and we can analyze EEG together as a whole signal, or we can analyze it by breaking into different bands. Delta, theta, alpha, beta, gamma. These are the different bands which we can break the EEG into different bands by using simple band pass filters. We all know what is band pass filters. Are you all aware? A band pass filters will will take a certain frequency range from the signal. Because some of you are not from electronics. If you want this delta band, you will have to pass your original signal to a band pass filter with cutoff frequencies 0.1 and 4. So it is something like this is coming, passing through a band pass filter with lower cutoff frequency 0.1 and upper cutoff frequency 4. Passes through this, and you get delta band. So filter is something which selects few frequencies and rejects all the other frequencies. So in this way, you can get delta, theta, alpha, beta, gamma. So the important point which I wanted to tell you is that not all sometimes you can analyze the whole EEG signal, but sometimes you can analyze only the bands. And these bands have some important connections. Okay. So these bands actually, like for example, alpha band. This alpha band is obtained when you are in awake state. Awake means not sleeping, but active, or you are awake. Then these frequencies will be more in your EEG. When you are sleeping, theta and delta will be more. So when you are sleeping, in the very initial stages of sleeping, alpha is observed. But when you sleep, you will observe theta and delta. When you are doing some mathematical calculation, problem solving, alpha and beta are also. So I simply want to give you an information that these bands are related to some specific functions or tasks. Okay, so suppose I want to do some sleep study, I may be interested only in alpha, theta, and delta. I don't want to analyze the whole EEG. I'm interested in these. If I want to analyze, say, patients of mental disorders, say schizophrenia or bipolar disorder, I may be interested in higher frequency. Okay, so depend. Eye blink is a noise. It is simply a noise. So the patients of schizophrenia and the patients with severe mental health issues, they may eye blink more, particularly schizophrenia. You will find more noise, eye blinks in their EEG. Okay, so generally when we do EEG experiment, I'll come to that. Just wait for 1-2 slides. Okay. There is another modality for analyzing brain which is called MRI. MRI simply gives images of the brain, but there is something called as fMRI, which is functional MRI, functional magnetic resonance imaging. So EEG is like this. EEG gives you information about what? It has a high temporal resolution. Temporal resolution means EEG gives you information about exactly किस time पे क्या हो रहा है. Amplitude versus time. It has high temporal resolution. If I am sleeping, if I want to do sleep stage analysis, then I'll have to record the EEG from, say, when you started sleeping at 10 p.m. So I'll need the EEG from 10 p.m. to till you awake at 6 a.m. Okay, so I'll need this temporal EEG. EEG has high temporal resolution, but in case of fMRI, it does not have high temporal resolution. It has high spatial resolution. It will indicate what? If I'm moving my right hand, which part of my brain is active. If I'm doing mathematical problems very fastly, which part of my brain is activated. This is good at spatial resolution, and this is good at temporal resolution. Exactly at particular time, what kind of signal I am getting. Both have different applications, but the advantage of EEG is that the EEG device is less costly. It is highly portable. You can take from one place to another place. Okay, and That's what written in the last point. It is affordable. 3 types of EEG studies are done generally. One is resting state. Resting state means subject is sitting on the chair, eyes closed, you are recording the EEG. Sometimes eye blinking can be done, but that is removed later on in pre-processing. Eye blinking is a type of noise. So resting EEG means subject is ideally sitting on the table, you are recording on the chair and you are recording the EEG. Then task based. I'm giving some task is being displayed on the screen. Say simple mathematical task, 2 into 4, 3 plus 3, and 4 answers are there. Subject has to select one answer. And we'll ask the subject that if you score highest, you'll get a good gift. So when slowly the task speed increases, I'm increasing like for the first 10 questions, I'll give 30 seconds for each question. In the next 10 questions, I'll give say 20 seconds for each question. So what will happen? As the task goes, the stress level of the subject will increase. This can be one experiment. Are you getting me? You can analyze that, how the EEG look, whether machine learning can classify stressed EEG and normal EEG. Such type of study is called task-based EEG study. And the third is event-related potential, ERP study. ERP is evoked potential. Evoked potential means what? I have a fixed stimuli. I'm presenting that stimuli to the subject, and subject responds to that specific stimuli. For example, I'll ask the subject that when listen some sound, multiple sounds, but when you listen this specific sound, press the key. You're getting me? Like for example, I'm presenting multiple sounds to the subject, and I ask the subject, when you hear the sound of bell, the temple bell, how then you press this key. There the what subject will do? Subject will concentrate only on that particular sound. And then the subject has to press the key when this type of study is called what? ERP study. In ERP study, generally you will get this type of graph. So these potentials are generated when the subject perceives the sound. Subject is in ideal state. You started presenting sounds. Okay. So P1 is the first positive peak at which subject perceives something. This is the first reaction. Then second reaction, third reaction. In ERP study, we analyze these things, that how much delay is there. It presented the stimulus, and this is the first peak. So after this much time, the subject responded to the subject's brain responded to this. So whenever the subject's brain will respond, there will be peak. So maybe in healthy patient, this response will be faster, and in diseased patients, this response may be slower. This type of study is called ERP study. This is the general process of EEG analysis. We acquire the data, we do pre-processing, I've already explained these things. This is how we record the EEG. These are the electrodes. These are the electrodes. There are some electrodes which are placed on this scalp. To place the electrodes, we use a standard rule which is called as International 10-20 or 10-10 system. ये हुआ है क्या यहाँ पे अभी? ये नहीं हुआ. So we use a standard 10-20 system. What it is, listen carefully. I have the 19 electrodes. In my lab, suppose there is a lab in IIIT Raipur, they also have 19 electrodes. Okay, they place it on scalp. I also place it on scalp. I record the data for the same task, for the same condition. If we do so, they should be comparable. Comparable means the data recorded from the positions my lab should be same positions at this lab also. Then only I'll be able to compare. So getting my point. That's why what researchers did, what scientists did, they fixed the point. ऐसा नहीं कि कहीं भी रख के रिकॉर्ड कर रहे हैं रैंडम, है ना. उन्होंने एक स्टैंडर्ड रूल डेवलप किया. व्हाट इज दैट रूल? That rule is called 10-20. In 10-10-20 system, what happens? So this is the node called Lejeune, and is the small bone that is elevated here on the back side. Below that. So we take a tape and we measure from this Lejeune to anion. Take a tape from this portion, from the forehead, this portion, and then exactly at the back side there is an elevated bone. We take a tape here, and then again we take a tape like circumference, we cover the circumference, and we divide this. Suppose the circumference is say 50 centimeters. We divide this whole region into ratios of 10-20. सबसे पहले देखो, this is 10%. So if this is say 50 centimeter, what is 10% of 50? 5. So this will be 5 centimeters. Then this will be 20%. So whatever is the 20% of 50. Then again 20, 20, 20, then last में फिर 10. So the first is 10%, then 20, 20, 20, again last is 10. Similarly from this side, this is 10% from year to year. 20%, 20%, 20%, 10%. Okay, then so this is one line and this is one line. Okay, and this is one circumference. Then after that, this is the intersection, right? This is the intersection. So again, the same process follows: 20%, 20%, 10%. I simply want to explain you that whatever easy caps you get from the market, they are designed with specific rules. Electrodes are not placed randomly. The rule to present. And this 10-20 can be either 10-10. Some systems also use 10-10. If you want electrodes to be placed more closely, you can also use 10-10 system. So when I say that when I write a research paper and I say that the data acquisition system which I have used is a 10-20 international systems, someone reading in America will know that what the kind of system I am using, so that they can compare my work with their work. Okay. Again, there are some nomenclatures. Can you see? F means frontal. This area is called frontal. Okay. Then C means central. This central area. Parietal. Parietal means this area. Okay. Occipital. पीछे सबसे पीछे occipital. Okay. Even numbers indicate this right. All the odd numbers indicate left. Okay. And why it is written this? Z is used for center. Z is used for center along with F. This is Z. Z indicates center, neither even nor odd. But right is even and left is. This is how we name different electrode positions. Clear now, everyone? These nomenclatures are clear to you. When you record EEG, when you place the electrodes on the scalp, along with the electrodes, there is a gel which we place between skin and the electrode to reduce the impedance. To improve the contact between what? Electrode and skin. We use a gel. And that gel helps us to maintain a low impedance. The preferred impedance is 5 kilo. Jitna kam hoga impedance, the quality of signal will be better. Okay. The EEG system which you get for recording, the cap which you get for recording, that is connected to amplifier, they are of two types: bipolar and differential. In bipolar, what we calculate, what we record is, we record difference between two electrode positions. Bipolar means what? This EEG amplifier is nothing but operational amplifier. I don't know how much about operation. Very basic terming for electronics. It has two inputs and one output, and output is proportional to difference between the two. Bipolar means two electrode positions are given to operational amplifier and we get the output. So for example, I can do say difference between FP1 minus F4, F4 minus F8. So I'll make pairs and their difference is recorded. The advantage of this is that noise will be less. Why noise will be less? Why noise will be less? is there. Yeah. This is bipolar and this is unipolar. Okay. In bipolar, so difference between these two is this. Difference between these two is this. So when you calculate the difference, you only see what is different. Means you only see what is change between these two electrodes. What is different in these? When two electrodes are very nearby, bipolar, you take two electrodes which are nearby. You record EEG signals from them. They will almost be same. It will almost be same. That's why we want to see what is different to bipolar. But if you're not interested in seeing the difference, we can go for unipolar. In unipolar, what happens? We make a fixed reference. We make a fixed reference somewhere, and then that fixed reference minus this, minus this, minus this. In unipolar, the reference is fixed. And in bipolar, there is no reference. It is pair between, it is difference between two electrode positions. Okay. So, like for example, if this is the scale, that's the electrode position. So in bipolar, I'll take this two, then this two, all paired. But in unipolar, what happens? I'll fix that this will be reference. And then I'll take this two, this two, this two, this two, this two, like that. Same will be reference for all. These are the different noises and artifacts which occur in EEG. The first is eye blink. The EEG looks like a very random signal. The blinks will appear to be elevated. This is how eye blinks look. Another noise is muscle artifact. It will be high frequency artifact, very high frequency. This is muscle artifact. It will look like this. Then we have cardiac artifact. In EEG, sometimes you see ECG-like pattern. Can you see here? The ECG-like pattern. This is called cardiac artifact. Then we have 50-60 hertz noise. What is 50-60 hertz noise? When you record EEG, this EEG is plugged into our supply which is coming. That is also recorded in the signal. It's called power line noise. The power line which is coming at my lab, that will also come in my signal. So we remove it by using notch filter. And then we have electrode noise. If the electrode is not fixed properly, if during recording, if it is moving, okay, then there may be deviation. It could come like a straight signal, but there may be, you can see, it is not straight, it is elevated somewhere. This is called electrode movement. So by this slide, you can simply understand that when we record biomedical signals, it has a lot of noises and artifacts. And the pre-processing stage, which I discussed in machine learning pipeline, actually is what? To remove these noises and artifacts. Okay. Yes, it is. Here reduces the impedance. So we were talking about impedance now. Lower will be the impedance, better will be the quality of the signal. The head is very hairy, so the impedance will be high. The quality will be less. Generally, when a subject comes for recording, start them to less oil and softer so that impedance. There is a gel. So it will no, but it will. We don't have to exactly keep it on the head scale. We have to keep here on. It's a limitation. That's why that so high impedance is there, 5 kilo. Okay, so we have to like when we place EEG, just a manual practice. Okay, we slightly remove hair like this from that position, then we whatever maximum we can. But hair has not to be. हाँ हाँ no. Okay, we're talking about some those images. That was only for clear understanding. Just for clear understanding. There would be hairs, you will not be able to see electrode part. What is the question? So, okay. First of all, it's not necessary that I always use 90. Our laboratory people. Okay. Many studies you will see where they have used one electrode on adults, single electrode EEG study, because we want to reduce the number of. Okay. So if I know that a particular disease, for a particular disease, occipital region is more responsible, I may use few electrodes in the occipital region and I can. So not always necessary. And for very newborn child, circumference of their head is very small. Okay. So obviously it will be very difficult to place 19. So there is no standard rule that any 5 electrodes are going to one. But we obviously will need fewer electrodes, not 19. And if they have some kind of abnormality that will be observed in EEG, that abnormality can be analyzed only by physician, not by us. Abnormality will be told by physician, then I will see whether in normal and abnormal EEG can I find some quantitative markers like P or something like calculate and probably ptosis, and I'll see if ptosis is different for normal and different for diseased. Okay, so the cap sizes, cap of EEG, they are different for children and different for adults. They are different for different heads. Hmm. 19 is standard. See, the aim is to cover the whole brain. So if you at least use 10 or 10 channel EEG is also available, but at least if you use 19, you will be able to cover the whole brain. You can use, because if you are moving only the hands, okay, only particular area for motor actions, only particular area of brain will be responsible. You have to identify that area and you can place the electrode. Like in one of our study with AIMS Raipur, they have 256 channel EEG. We got 256, but then we extracted only the EEGs of few regions, which were responsible mainly for schizophrenia. Okay. Any more question? So I told you, so the one is like you can give some kind of audio input, some kind of sound. Other is flash of light. These are examples. There can be multiple stimulus, any form of stimulus. One is flash of light. Like whenever you are produced with flash of light, press the key. Whenever you see letter L on the screen, press the key. Any kind of stimulus. No, there is no such standard. We will see studies with 1 minute EEGs also, particularly in the resting state. In resting state, you are not giving any task. You want to do some resting EEG study. So though I may record 5 minutes, but I recorded 5 minutes because I needed more number of samples. Later I segmented it into 1 minute. Sometimes it depends on the task. Like I have given some mathematical task. Your task duration is 3 minutes. You will have to record it for 3 minutes. EEG is completely harmless device, because you are simply so what harm it can do is, like suppose when we do recording in AIM, sometimes the patient becomes uncomfortable just because you are placing so many wires on the head. Okay, and it takes time to set up. You put gel on the electrodes and then you adjust the impedance, so that I want my impedance to be very low. So I put the gel in the electrodes so that the impedance is less. This takes little bit of time. At least minimum 15-20 minutes will take just for setup. So because of these things, the patients may get uncomfortable first. They may lose patience. Second is that sometimes these gels which we used, the patients may be allergic to that. Some subjects may be allergic to that. But that can be cured by just first aid device like some kind of anti-allergic. There is no major harm. It is completely non-invasive process. Okay. For that you need EM. But everything, whatever is happening in our body, it is reflected in EEG also. It may be hard to reflect. But generally for muscle related, we use EMG. Okay. But there may be some changes in EEG also. Somebody can try that also. This is the general approach by which we can analyze EEG. We do some kind of manual inspection first. We'll see ki kahan pe blink hai. So we can remove it manually also by removing it. We can do filtering, denoising, all these steps are there. So when we do this signal analysis, either EEG or pulmonary sound or whatever, base started with what's Fourier transform. First signal processing technique is what? Fourier transform, which is repeated. What is the drawback of Fourier transform? So many electronic people are here. Can you tell me what is the drawback of Fourier transform? It is not good for non-stationary signal. Why? So I just skipped one slide. There is something called as stationary and non-stationary. Stationary signals are the signals whose frequency components do not change with time. They are stationary. The characteristics do not change with time. What are non-stationary signals? Their characteristics, that is frequencies, they change with time. EEG you just saw, na, it is very random. The frequency is not constant. Okay. So a simple sine wave like this is like this, because its frequency will not be constant over time. Fourier transform was good to solve stationary signals. Because it was good to solve problems which were stationary. But for non-stationary signals, Fourier transform is not good. What is the main drawback of it? A signal of finite length is expressed as the sum of frequency components, right? Duration. Okay. It fails to provide the exact location of the event. Now just assume that this is a simple sine signal, but with 3 frequencies. So there are 3 frequencies. One is this. Can you see? This is a different frequency. This is a different frequency. And this is a different frequency. Same signal with 3 frequencies. Which one is higher? Suppose F1, F2, F3. Which one is higher? F2 is greater than 3, then F. When you calculate its Fourier transform, you will get 3 peaks. Because there are 3 frequencies, you will get 3 peaks. This is F1, then this is F3, and this is F1 is lowest, so it will come this side. Then F3, then F. There is a difference between both, right? Like, even if assume that this is not available, and if I give you this Fourier transform, the Fourier transform will be same even if F3 is this side, F1 is this side. Second point, it fails to provide the exact location of the event. Here, F2 is coming in middle. The location is in middle, but here it is coming in the right side. It fails to give the exact location of the event along the time scale in the frequency domain. Okay, that is the problem with Fourier transform. That problem was resolved using short time Fourier transform. I'm not talking in much detail Fourier transform. I hope all of you might be aware of it. Little bit. So the formula of Fourier transform is what? The formula is xt e to the power minus j omega t dt. This is the general formula of Fourier transform. What is the change here? Additional component is there, wt minus t dash. This is the additional component. In short time Fourier transform, what happened? That this type of sinusoidal signal can be broken into small pieces like this and then calculated Fourier. That's why it is called short time Fourier transform. break the time into short period, then calculate the Fourier transform. This breaking thing is taken care by this Wt minus T dash. Okay, first the window will be, W is the window. First it will be here, then shift it here, then shift it here. So T dash takes care of shifting. T dash will be initially 0 and it is here. Then shift by 1, window will be here. Shift by 2, window will be here. So the drawback of Fourier transform, which we studied in the previous slide, is resolved using short time Fourier transform. But the problem with short time Fourier transform is that the window length was fixed. Window length was fixed. So because this window length is fixed, sometimes there may be a possibility that even within this window, there may be multiple pigments. Like in EEG, even in small window, there are multiple pigments. That's why to further resolve it, what was introduced? Wavelet transform. So what is the equation in wavelet transform? This is the equation. Xt is the signal, and then there is a mother wavelet, which we call it as 0 by psi, whatever. And we add two parameters here. Shifting, which was there in STFT. Now is the shifting parameter, which was also there in STFT. But other than this shifting parameter, we add a new parameter S, which is called as scaling parameter. What this scaling does? Signals. If this is a signal, to scale it by 2, it will compress by 2. If you scale it by half, it will be expanded by 2. I simply want to explain you that this scaling actually, this scaling will change the window length. STFT में window size क्या था? Fixed था. To control that, we added another parameter S, which will control that window width. It will not be fixed. But the problem in wavelet transform was that here we had to choose something called as mother wavelet. Psi is called mother wavelet. What is mother wavelet? In short time Fourier transform and Fourier transform, we were representing all the signals in terms of sinusoidals, right? E to the power minus j omega t is what? Cos omega t minus j sin omega t. But here we don't represent them in terms of sinusoidals. We represent them in terms of mother wavelets. So psi is simply a different function. E to the power minus j omega t was a different function. Here this psi is a different function. There are many mother wavelets. You can just look out in some text. Like for example, Haar wavelet is there. Electronics people might have heard this. Haar wavelet is there. Bi-orthogonal wavelets are. So these are some other functions, and signal is represented with in terms of these functions, not sinusoidal. But the problem with wavelet was that this choice of mother wavelets was very difficult. There are so many mother wavelets. Which mother wavelet I should use? And sometimes what happened, when you choose that mother wavelet, the mother wavelet may not be very much correlated with xt. They may not be very much correlated with xt. To address this issue, the main problem was the choice of mother wavelet. To address this issue, what happened? To address this issue, can you name some new techniques? What came after this? I think you might have covered it in first or second day of the STTP. So one is Fourier Bessels taken by Pachori sir. And what other? एक अच्छी फोटो ले लेना यार, है ना? What others? एक अच्छी फोटो दे देता हूँ, नहीं तो फिर बार-बार डिस्टर्बेंस होगा. So you have heard empirical mode decomposition. You have heard empirical wavelet transform, relational mode decomposition. All these are new techniques used after wavelet. So those who are doing study in signal processing technique, we should know these techniques. In air technique, Fourier decomposition. Initially, we saw that Fourier decomposition is not good for analysis of non-stationary. But later, people proved that if we do some minor modification in that, we can also सिग्नल प्रोसेसिंग में जो लोग काम कर रहे हैं, they should not start studying from Fourier transform now. These are very old. Start from EMD, BMD, EWT, Fourier Bessel, Fourier decomposition. Pardon? Yeah. So that is from after doing wavelet decomposition, we calculate Shannon entropy. That is the feature which is obtained. Okay, like we studied, entropy is one feature. So similarly, there is a feature called as Shannon entropy. It is based on entropy, but slightly different from the original entropy. Okay. So I think here, I told you. So we studied about pre-processing. Okay. Then we studied about signal processing techniques, old signal processing techniques, and I told you about new signal processing techniques. Then these are the EEG features. We have already discussed. I'll just name them. Time domain features can be mean, standard deviation, skewness, entropy. Similarly, we can have frequency domain features like power spectral density. Means first calculate the Fourier transform and then calculate power. So it will be called spectral power. Without Fourier transform, if you calculate power, it will be simply power. After Fourier transform, if you calculate power, it will be spectral power. So these are the features obtained after Fourier transform. And we can have some synchronization features like correlation, coherence. In EEG, there are multiple channels. I can use another feature called as correlation between two channels. That is also a feature. And we have many other features. You can see it later on. These are the clinical applications of EEG, which we are working in our laboratory. Okay. Very briefly, now the third part, which is, so we have till 15 minutes. So I'll be discussing computerized diagnosis of asthma and COPD using machine learning. Okay. So I'll simply come to my two papers. Okay, I'll first discuss the motivation. Now you all know that, you might be knowing that asthma and COPD both are the diseases with similar similar symptoms. Okay, in both asthma and COPD, patients feel similar symptoms, like there will be shortness of breath, there will be tightness in the chest, they will feel tightness in the chest. Okay, so whenever somebody is suffering from asthma or COPD or any such disease called blockage of airways of the lungs, okay, the patient goes to the doctor, test that is conducted called pulmonary function test. It is done through spirometry. Where you will be asked to inhale and exhale. So that spirometry actually measures how much air you can inhale, how much air you can exhale. So indirectly, it measures your lung capacity. It is called as pulmonary function test. It is done through a device called as spirometry. Okay, that is the gold standard. That is the test which is done. But the problem with that test is, so there are two problems. One is that there are common symptoms, which is written on the slides. Asthma and COPD subjects have common system, and pulmonary function test sometimes is not accurately performed, especially by children and pregnant women. Okay, because you have to forcefully exhale and inhale with the highest possibility, with the highest capacity you can. So PFT is not always suitable, particularly with diseased patients, with patients of with children and especially pregnant women. Okay, so we wanted to develop some alternative technique to categorize COPD and asthma. So as you can see in this slide, that asthma and COPD both have coughing symptom, shortness of breath symptom, chest tightness symptom, wheezing sound is there, anxiety is there. Okay. And what are the existing problem? I told you that the existing method is what? Pulmonary function test. Okay. So this test depends on largely on what? Skilled technician. The test cannot be done by me. There should be a paramedical staff or the technician. He will guide me, and then only I'll be able to perform the test. Okay. Then the other thing is what? It is very difficult for children and pregnant women. Okay. So to address these issues, we proposed a computerized machine learning and deep learning approach to classify COPD and asthma. For that, we recorded our own data from AIIMS Raipur, and to record the data, we used a Littmann stethoscope. It is an electronic stethoscope.
Along with the pulmonary sounds, along with the lung sounds, we recorded additionally these data like subjects, past medical history, pulmonary function test ka kya result aaya, that also we recorded, and then we recorded lung sounds. Okay, so these are the some of the informations which we obtained. If you all are doing some study, you should record these informations also in your study, like patient's name, gender, age, height, weight, qualification, occupation. Now, how qualification plays role here? Can you tell me? In general, how qualification plays role, like in this asthma and COPD, qualification may have minimum, but whatever I am guiding to the subject should be able to understand. Particularly in EEG, where you are doing some task-based experiment. Just try to recall that I told about mathematical task, problem solving. Even if I'm doing simple math, the subject must be at least 8th pass or 5th pass. I have to take this information also. Okay. Then martial status, duration of smoking habit. So these so many different parameters are taken, and we also take spirometry details. Spirometry details means when you do pulmonary function test give you this FE1, FVC. So what are these? I'll be taking in the next slide, probably next slide. So what is pulmonary function test? It is a respiratory test for detecting lung capacity and okay, so there is a process also there. I'll skip that. So we recorded the lung sounds. The posture was sitting straight. The subject was asked to sit straight. The recording position was posterior base, both right and left. So we didn't recorded the lung sound from the front, because if I record the lung sound from the front, heart sound will dominate. Recorded it from the posterior side, back side. This okay, they were recorded it from the 4 positions from the back side. Okay. Then recording time was 20 seconds, and pattern of breathing was what? Inhale deeply and exhale deeply. Means we asked the subject to inhale deeply and exhale deeply. Okay. This was the inclusion and exclusion criteria. So whenever you are doing any kind of medical research, not only in context to this study, you must first decide 2 things. One is the recording protocol. One is the recording protocol. So what was my recording protocol? This: sit straight, then inhale deeply and exhale deeply. In case of this, it is such a simple recording protocol. But in EEG and other studies, there may be a 20-minute recording protocol. So first 10 minutes में क्या होगा, फिर 10 minutes में क्या करना है, फिर 10 minutes में क्या करना है. You have to design a protocol like this. And after that, you have to clearly decide in your on paper whom you will include and whom you will exclude. So this is called as inclusion and exclusion criteria. This is the inclusion and exclusion criteria for control group. Control group means healthy group. Okay. So like for example, the age group should be between 18 to 60 will be included. The body mass index should be less than equal to 24. So these, from where these values comes, why I'm taking 24, it is considered to be healthy. Okay. No, not taking any drug or medication. Both male and female are allowed. Absence of history of smoking. Then similarly, whom I will exclude, I will not exclude children, I will not exclude older or greater than 60. Those suffering from cold and cough, but still if they don't have asthma or COPD, then also if they're even if they are healthy but they have cold and cough, I will not include. Okay. History of any disease like hypertension, respiratory disease, I will not include. Pregnant women, I will not include in data recording. Similarly, for asthma group. Similarly, you have to decide exclusion and exclusion criteria for. This is very important when you do medical research. Clearly define your exclusion and inclusion and exclusion criteria. Okay. These are the steps of data collection. We took spirometry data also. Then I have already discussed the subjects were asked to sit straight and then breathe in and breathe out for 10 seconds. So 20 seconds approximately. Okay, this is already covered. Now I'll discuss what we did with this data with the help of our papers. The first paper was respiratory sound-based classification of COPD. So this study was on COPD, a risk stratification approach
in machine learning paradigm. So what we did in this study, up to here I have explained you how to divide the data into training and testing. The board. Training data was, so the data here was what? Respiratory sounds. So respiratory sound was first denoise. For denoising, I use one filter called as Schmidt-Gole filter. There are 20, n number of filters. You can use adaptive filters also. In adaptive filters, because the primary reason of filtering this sound was it always include some part of heart sound. So always include heart sound. It will not dominate in the when you record it in the posterior side, but it will dominate when you record it from the front side. Okay. So to remove that noise, to remove some other noises which occur due to instrumentation and other things, we need filters. So we use the standard filter which is called as filter. Then we did normality test. I hope you can recall with what was taught earlier. We used normality test. We did statistical significance analysis. It was not normally distributed, so we used Mann-Whitney U-test. Though we also reported the test, the results of t-test. But t-test is not used when the data is not normally distributed. Okay, but we may use it. But the standard practice is to use Mann-Whitney U-test when the data is not normally distributed. Then we did feature extraction. This is feature extraction. Identification of reliable biomarkers means we extracted some features and now we want to determine which features are reliable or which features are more useful. Then we did training. Training, too many different classifiers were used. Here discriminant analysis, logistic regression, KNN, support vector machine, decision tree. And then this was the ground truth. Ground truth means label. Label was present here. Label is also sometimes called ground. Okay, so the ground truth was available, and based on that, we trained the model and we got the machine learning parameters. So, what are the machine learning parameters here? Weight. Got the standard weights after doing the training. Now, this trained model was taken in the testing side. Same model is used. New data, that is the test data, was provided. Only reliable biomarkers or features were extracted. All the features were not extracted. Only relevant features were extracted in the test module. Then classification was done between PD and healthy, and we were able to get good results. This was one study which we did. The second study which we did was a real-time correlation model between lung sounds and clinical data for asthmatic patients. In this study, we recorded some data like you can see in this diagram. So we recorded the lung sound data. Along with the lung sound data, we also recorded the clinical parameters. So what are the clinical parameters that I have already taken in the previous slide? You should record all the data, and we extracted different features based on wavelets, based on Fourier vessels, based on MFCC, then I vector. And then we wanted to calculate a correlation between these extracted features and the clinical conditions of the patients. So here you can see FEV1 and FVC. So this is called force vital capacity. This is called force excited volume. These both are related to the capacity of lung to inhale and exhale capacity and their ratio. These three are obtained from pulmonary function test. We have not done anything in that. The technician sitting there performed the PFT, spirometry, and they gave us these three. These are the other data which we recorded. Okay, and these are the clinical symptoms like ongoing cough, increase, mucus, shortness of breath, breathing, fatigue. And the correlation between these parameters and the features which we extracted, wavelet, Fourier, MFCC, and I vector. We analyze that correlation. For example, if the correlation is 0.98, it means that MFCC was very much correlated with the pulmonary function test data. See 0.98, 0.95. So with these two, it is highly correlated. Okay. In this way, we did correlation analysis and we tried to find out that the clinical symptoms, the pulmonary function data, how they are correlated with the features which we extract in signal processing field. And there was good correlation obtained between some cases. The another correlation analysis which we did is between the, so this is correlation analysis fatigue, shortness of breath. So this is what the symptoms, symptoms of the patient. Whether the patient feels fatigue or shortness of breath or ongoing cough, age, weight, etc., and how they are correlated with the condition of the patient, that is asthma. So again, you can see that highest correlation is 1, and somewhere we were able to correlation like 0.9. So these indicates that fatigue, shortness of breath, ongoing cough, they may be they are obviously seen in asthmatic patients. Okay. These are some of the other studies which we are doing in our laboratory. The first is breast cancer classification. Recently, one of the candidates from our lab, Kushangi Atre, she submitted her, she is awarded recently. She did her work on multimodal breast cancer classification. Okay, so most of the existing work, they use unimodal breast cancer classification. Unimodal means they take one modality like X-ray or ultrasound, okay, and they did classification. She did multimodal classification in which along with mammogram means X-ray of breast. So X-ray, ultrasound and clinical parameters of the patient. These three informations were combined to reach to the decision. So the machine learning and deep learning model was uh, not only trained with one type of feature, not only ultrasound feature, not only X-ray feature, but the combination of all those. Okay. Then lung nodule classification we are doing EEG based some studies like mental illness, schizophrenia, Parkinson's, epilepsy we are doing. We did few time back about the detection of COVID-19 using X-ray or CT. Okay. With this, I will stop. If you have any questions, please ask. I'll stop my talk here. Any more questions? You have asked many questions, but if some of you, I think we were discussing that time, we didn't have time. A few candidates, somebody I wanted to ask that time. So it is very simple. We had a electronic stethoscope in our lab. Okay. That electronic stethoscope was placed at the site of recording. So I already told what is the site of recording, posterior, this side, positions, 4 positions. So we simply placed it there, and the patient was asked to completely inhale and exhale. So in that way, we were able to record the lung sounds. This is the only thing which is, so it is the simplest signal which we can record. Initially, they were like for first 5 samples they saw, but then we recorded by ourselves. We went there and we were recording there. PFT expert was there. So first PFT was performed. PFT values were recorded. After that, lung sound was recorded. Littman electronic stethoscope. This, yes, it is an electronic stethoscope which has an interfacing with your computer also. So you can store your data here in computer. You can then analyze it further. So this was done with Dr. Behra sir. Behra sir, he was co-guide in this study. Hmm. Ready-made, sir, ready-made. But now in one project, we are developing low-cost version of it because it is around. If you take good one, it will be around 1 lakh, 80,000 to 1 lakh. The normal stethoscope comes 700. The doctors which they use, that is 700, 800. But that is electronic stethoscope, so it is bit costly. So in one project, in one SRF is there, he is trying to develop it, low-cost version. Okay. So there are 2 ways to do it. Okay. One is you just refer the previous study. That is the simplest way. But obviously it may not be always correct. The another way is 2 things are important to calculate the sample size. One is the incidence of that particular disease. Like if I am working on breast cancer, I'll see what is its incidence in India. What is the how much percentage of population suffers from breast cancer in India. That is one thing. And I can otherwise, if I'm doing some pilot study, I can take state incidence also, any one of them. Okay. And the other thing is how much accuracy you require. Previously I talked about confidence interval. Okay. So then you have to see this is the simplest way I'm telling you. There are other methods also. You can just, you will see many research papers, how to decide a sample size in clinical research. Just type in Google, you will get many things. And the second is, what I told, incidence and accuracy, like 95%, 99%. Higher we want the accuracy, more we will need the sample size. So when these two variables are available with you, there is coherence formula. Okay, you can type in Google. You'll get that. There is a automatic like we have automatic calculators in Google now for so many things. You will get there is automatic calculator. You will put these two values, you will get the number of samples required. But you read this thing, how to calculate the sample size in clinical research. Standard device. Yes. So in that case, you can simply again for that there is no such rule. You take some recordings from the standard device, some recordings from you under different conditions. Like for example, if I design a stethoscope, I will take from normal subject, asthmatic subject, 10 samples from all the different. I'll have to take the data from different environments and then I'll have to compare. But there is no rule for that. But it is expected that it should be a bit higher, like at least 40 samples from each condition, each environmental condition. Okay. Calculating the impedance. Yeah. So whatever EEG machines you will acquire, they have associated software which is installed in the computer. So while placing the cap, EEG cap, while putting the paste and everything gel, automatically the impedance is shown on the screen because the signal is transferred there, na? So that yes. Okay, so in case of why I talked about EEG is that EEG is the most random biomedical signal, but that is not in the case of ECG or EMG. In EMG, you have to use surface electrodes. You can simply use gel. That is accepted. Whatever impedance is coming, that is accepted. In ECG, the quality of the signal is already very good. We know the standard range of QRS. In EEG, we don't know all these things. But in ECG, you know that QRS should be, the peak of QRS should be in this range. So that is more important than the impedance there. That impedance thing is taken care by the device itself. Okay. Yes. Yeah. So I told you that the signal which we get from one electrode, it is not actually from that position only, right? We have that is because of the firing of several neurons surrounding that location. It is very difficult to localize the source of that EEG signal, exactly from where it is coming. So if you have more number of electrodes, that source localization becomes easier. That is for one thing. Okay. Because I told you now, when you do this bipolar EEG, you see the difference. So if you have more number of electrodes and you use bipolar, you can easily see how close, where the difference is and where there is no difference. Okay. Second thing is that so many neurons are there. If you use more number of electrodes, like if I want to analyze only say occipital or central region, more closer will be the electrodes, I'll get more accurate phenomena. Means it is actually related to that source only. If they are closer, we'll say that this particular signal, when you do bipolar EEG, then whatever output you are getting, it is representative of that region only, that position only. Obviously, spatial resolution will improve. Yeah. Yes. Yeah, so that has been obtained experimentally. That signal quality with at least 5 kilo ohm or lesser is acceptable. That is just an experimental, but obviously doesn't mean that 10 k ohm is not good. We can do with 10 k also, but it is generally acceptable cutoff obtained with different experiments. Okay. Any more questions?
So thank you so much, sir, for your insightful discussion and the explanation about the machine learning as well as the biomedical signal and all the things. I hope it will helpful for the all the participants. Now I request Dr. Anurag Singh sir to please felicitate with the token of appreciation to Vikesh sir.
Okay, so let's all join hands to thank Dr. Vicky sir, who come across, from NIT to here to deliver this talk physically. Thank you very much, sir. Thank you very much. You have I think not from NIT. I think I came across from Vilay, 2 hours it almost took. So thank you very much for taking this pain, sir. And so I was not there present in most of this session, but yes, by seeing this board and all, it seems that in-depth discussion happened related to machine learning and all. Sir is from biomedical engineering department, but so nicely he covered this case study highlighting this ML part and both this disease part or what is the lung sound detection sir is doing. It was very nicely, and I hope it will be helpful for all of you. Okay, thank you, sir. Thank you very much once again.
So a small announcement for you all that we will start the lab session around 2:45 in that same lab, data science. So no need to come here directly. You all need to go there. Okay.
Next session is, I think, practice, right? Practice session.